This video is going to show how to run basic regressions in R. So let's use the Click ballpoint pens dataset, which is available from Blackboard. And I've already read this in. So here is the Click dataset. Let's do a summary on it. What you're going to see is that it has about 7 variables. This comes from some hypothetical company that makes ballpoint pens. This company has 40 different sales territories, and you know the sales in each of those territories during some period. You also have, so sales is the variable that you like to explain. It's the dependent variable, the criterion variable, and you have a number of variables that are thought to be causally related to this. So in other words, you've got some variables that measure things that will affect your sales. So one of the things is you know how many advertisements you ran on television during that period. You also know the number of sales representatives that you have in the field, and you distribute these pens through some wholesaler. And different wholesalers in different territories have different levels of effectiveness. So some are outstanding, that's a 4. Some are good, some are average, and some are poor. So that's what this effectiveness variable is. We're going to ignore the last 3 variables until a later time. So then the question is, how does advertising, the number of reps, and the wholesaler efficiency affect sales? Now, the reason you might care about this is that you have to allocate resources. So next period, you're going to have to figure out how many ads should I put in the air, how many sales representatives do I really need in that territory, and should I invest in getting a better wholesaler if my wholesaler is not so good? So it's really a resource allocation question. I want to know if I change my investment level in any of these, how does that affect sales? Well, let's start out with a correlation. So to get correlations in R, you just type core and then the data frame. Now, I said I really don't care about the other columns, so let's just use columns 1 through 4. And here's your correlation matrix. I think R gives excessive decimal places on this, so I often like to round it. So here is the correlation matrix. Now what we really care about is the relationship with sales. And so we see that, well, advertising has a correlation of 0.88. What that means is that as we increase ads, sales go up. Reps also have a correlation of about 0.88 with sales. So as we increase reps, sales go up. Wholesaler efficiency is virtually uncorrelated with sales. So what that indicates to us is that it doesn't matter what type of wholesaler we have, whether it's good or poor or outstanding, the sales are going to be about the same. Now it always helps to visualize this. So you can visualize it, as I show on the next page, with a simple plot command. So if we just plot click sub one through 4, give me the first 4 columns, you get something called a scatter plot matrix. So let me walk you through what this is. This gives you scatter plots of every possible pair of variables. So this plot shows the relationship between sales and advertising. So this is telling the same story as the correlation coefficient. As we increase the number of ads, the sales, the mean level of sales, increases. Now another thing to note about this scatter plot is that it looks like there might be a little bit of heteroscedasticity going on. So notice the spread down here seems to be a little bit smaller than out off on the right. We may want to address this in a future lecture, but for now we're going to claim it's not a big deal. Now this next plot shows the relationship between reps down here. So this is reps on the horizontal axis and sales on the vertical axis. And you have a very linear relationship This is a textbook linear regression relationship. Strong positive association. The more reps you have, the higher your sales. The final plot shows wholesaler efficiency and sales. And just as the correlation told us, there's very little relationship. So if you had a poor wholesaler, here are your average sales. If you had a fair, well, maybe it goes up a little bit. If you had good, maybe it goes down a little bit. If you have outstanding, maybe it goes up a little bit. But there's very little relationship. So as always, you can use graphs to understand the story. You can also use single number summaries like a correlation coefficient to understand the story. And so often those two complement each other. Now let's run a regression. At this point, we're only going to be concerned with the advertising variable. So to run a regression in R, everything is done with the LM function. So I'm going to make a new fitted object, and this is going to be the result from calling this LM function. The first argument is going to be the formula. So the formula is always the dependent variable, tilde, any independent variables that you want. Now, this is simple linear regression, so we'll just do one independent variable. The other thing that you have to do is give it another argument, which is the data frame. So this is a data frame called click. And you have to spell LM correctly. It's LM, not LN. All right, so now we have our fitted object. If we do a summary unfit, we get various output. So let's take a look at what's in this output. There's a couple things that are very important. Where to start? Let's start with the overall test of significance. Now, this overall test of significance is not very interesting in the case of simple linear regression, but it will be interesting when we get to multiple regression. So here's the statement of the null hypothesis. So the overall significance of the model really asks the question, do any of my predictor variables explain why? So the way to state this in a hypothesis is the null will be all my betas. Now in this case, there's only one beta. So the beta for advertising is equal to 0. So if the beta is equal to 0, what that means is a change in advertising produces a change of 0 in sales. In other words, there's no relationship, no linear relationship between advertising and sales. The alternative for the overall test of significance, it's sometimes called an omnibus test of significance, is that at least one of these betas, now in this case we only have one beta, but at least one of them is non-zero. So the way we test this hypothesis is to go down in R to the last line. This is tested with an f-test. And so the f-test in R is reported in the last line. Other packages like Excel move it further up. And the p-value you'll see is down here. It's 0.13 zeros and then 732 something or other. Now, since this p-value is so tiny, it's way less than 5%, we're going to conclude that the data that we've observed could not have been observed if the null hypothesis had been true. Okay, so if the null were true, the chance that we would observe, this data, that has this much relationship or more with the dependent variable, essentially can't happen. Therefore, we reject H0 and conclude that at least one of these betas is non-zero. Now, let's interpret the parameter estimate. So usually when you interpret a regression, you do this omnibus test first. And if the omnibus test is not significant, what that's telling you is there's nothing going on. You might as well stop, this regression isn't going to get you anywhere. The fact that we've rejected the overall test means that this regression is doing something. We might as well look at the other results in here. Now, if you recall, regression gives you three numbers that summarize a scatter plot. So here's your scatter plot. We're going to summarize that with three numbers. So the three numbers are a slope, an intercept, and then the standard deviation of the errors. So how much spread is there in sales conditional on some value of advertising? So where are those three numbers? Here they are. So here is the estimated intercept. Below that you have the estimated slope. So we can say that the equation of the regression line that passes through the middle of the data is this. It's going to be 135 plus 25.3 times ads. So what does 25.3 tell us? That's a very important question. So what that tells us is that for every additional ad, on the average, sales increase by 25.3. So let me repeat that. For every additional ad that you put on the air, sales increase by 25.3 on the average. So that on the average is really important. It's not like you're guaranteed 25.3. Instead, it's on the average. So if we go back to one of these scatter plots that I had earlier, so if this were advertising, you notice we have this spread, right? So if we increase ads by 1 unit, so notice the regression line increases by 25.3. That regression line summarizes mean of sales. So the mean of sales go up by 25.3. Okay, the third parameter estimates how much spread there is around that line. So it's an estimate of the standard deviation of the errors. So let's go take a look at that now. You find that number down here. It's the residual standard error. So the residual standard error is about 60, so 59.56, indicating, we have these normal distributions around the line, and that normal distribution has a standard deviation of about 60. Let me show you how you could plot this. First off, I'm going to plot click $ad on the x-axis and click $sales on the vertical axis. So now you'll see a nice scatter plot. We can superimpose a regression line by saying AB line fit. So fit is that fitted object. And so now we can actually see that regression line, and we know that the intercept is 135 and the slope is about 25. And what we observe from the scatter plot is that it gives a pretty good fit to the data. This line passes pretty much through the center of that scatter. So this is not bad. Let's move on. Another question that we may have is about sampling variation. So we've estimated that the slope is 25.3, but if we'd observed a different sample of data, maybe we took the previous quarter rather than the quarter we've got, the numbers would be a little bit different, and therefore the estimates from regression would be a little bit different. So how much might that slope estimate change? So that slope estimate is really critical, because it's saying, what do I get for an extra ad? Well, how much is that going to change if I'd drawn a different sample of data? There's really two approaches to this, two ways of getting the confidence interval. One you want to know about, well, actually both you want to know about. Remember that confidence intervals, 95% confidence intervals when you've got reasonable sample sizes, are just two standard errors out from the mean. So here's the standard error, and here is the slope, 25.3. So you're going to note if you go two standard errors out you hear those numbers, it's really about 21 to 30. So between 20.9 and 29.7. That's what you think the true slope is. Now we should be using a t-distribution. We've got a fairly large sample size, so the results will be close. R will compute, so the second way to get these confidence intervals, in addition to just going 2 standard errors out, is to use the compint function in R. So if you say compint fit, R computes this with the t-distribution, and this is more correct than just going 2 standard errors out. And you'll see that we're really close. So here we used, the normal value rounded to 2, and you see 20.82 versus 20.9, and then 29.79 versus 29.7. So it's close. All right, so in order to run regressions, you definitely want to be able to state the estimated regression equation, find some confidence intervals, be able to plot it. Another thing that we usually want to do is to test whether individual slopes equal 0. So slopes equal to 0 indicate that that variable has no effect. So if you think about if advertising had a slope of 0, what that would mean is that a change in advertising would produce 0 change in sales on the average. All right, so whenever this null hypothesis that the beta is 0 is true, that means that variable doesn't have a linear relationship with sales, and usually that means we just can ignore it because it's not telling us anything. So how are we going to do this? It's such a common task to do this test. R and every other regression package on the planet gives you the p-values for it. So here is the p-value. It's 7.33 times 10 to the minus 14th. So that's a bunch of zeros and then 733. Now, what that's really saying is that if the null hypothesis were true, the chance that we would observe a sample that gave us a slope this large or larger couldn't happen. One chance out of 10 to the 10 to the 15th or 14th, whatever that is. Let me draw this. So this is going to be the sampling distribution. Maybe I should be using a different color. Let's go get some black. Here's the sampling distribution of the slope. So here's the distribution of B. Now, at the end of the lecture, I said that these slopes have approximate normal distributions. So this is going to be the distribution of B. Now, whenever we do hypothesis testing, we begin by assuming the null hypothesis is true. So if the null hypothesis is true, remember I said that the expected value of B is whatever beta is. So here we've said beta is 0. Therefore, the mean of this distribution, let's sketch that in, is at 0. So if we assume H not true, then the mean of this is 0. Now what we've done is to go off and gather 40 observations, and we computed the amount of relationship between them, and we found that the amount of relationship is 25.3. And all of this problem is going to cook down to us finding the area in that tail. So this is a two-sided test. There's really another tail out here someplace that starting at minus 25.3. The combined area of these tails is that 7.3 times 10 to the minus 14th. So you could say that 7.33 times 10 to the minus 14, was it? I think it was 14. divided by 2, okay, is the area in this tail, and it's also the area in that tail. So if you combine those two tails, you get a grand total of 7.33 times 10 to the minus 14th. And that's exactly what's given on the output and on my slide. So because that's so small, we reject H0 and conclude that beta is not equal to 0. This is exactly equal to what we had for the overall test. And that's not a coincidence. It's mathematically always the case that this overall test will exactly equal this t-test for an individual coefficient when you only have one predictor. Okay, so that's another thing that we want to do. So we now conclude that sales affects advertising. So if we advertise more, we will get higher sales. The last thing that you need to be able to do with regression is make forecasts. So remember last time I said that regression has two applications, interpretation and prediction. So this hypothesis test is really the interpretation part. We want to know if I change my advertising by a certain amount, what happens to sales? The answer is 25.3, and I know that that thing's not 0. That wasn't just a sampling fluke. Okay. The other thing we use regression for then is forecasting or prediction. So let's say that I want to put 5 ads on the air in some territory next period. What do I think my sales will be? So I need to have enough product out in the field to cover the demand that I generate from my advertising. So the answer is quite simple. I would expect sales. So y hat, recall, gives us the point on the line, which is the mean, right? Is going to be 261. So if we go over to here, if I put 5 ads on the air, I expect my sales to be that point on the line, which is 261. Now notice there's variation around that line. We know that the standard deviation of that distribution is the standard error of the estimate, or 60. Okay, but I expect sales of 261 or 262, I guess, if you round correctly. You can get R to do this computation for you. So if you say predict is a very useful function that works with any model in R. And I have to specify a data frame. And so let's say ads it equals 5. And sure enough, we get that result. If you wanted to produce a range of values, so let's go 5 through 10, you'll see that you get predictions for all of those values. Now, this 262 gives us the mean, but we might want to think a little bit about the variation around that. So there's a couple additional results about those predictions. So unlike slopes and intercepts, where you only have one confidence interval, when it comes to making a forecast, we get two different two different types of intervals. So let me explain the difference between these two. So one type of interval is called the confidence interval for the mean prediction. So what that's saying is I've estimated my sales to be, well, 262 if I had 5 ads. How much sampling variation is associated with that mean estimate? So if I'd estimated a different regression model, how much might that mean estimate change? And so that's called a confidence interval for the mean prediction, and there's a formula for that. I don't really expect you to know the formula, but here's the R code to generate one of those. So let's type that in. I've just added an extra argument to the predict function, and so here we see what the fitted value is still 262, but the value could be as low as 229 or as high as 294, 295. So that gives me a little window for what I think the mean is. So that's what a confidence interval for the mean sales involves. Let's take a quick look at the standard error formula for this. So remember what we're in essence doing is going 2 standard errors out from the mean. So that's what this this formula was. What factors affect this? Well, first off, the sample size affects it. So as the sample size increases, notice the standard error gets tighter and our estimates get more reliable. The amount of variation around the regression line also affects this. So the more variation, the less reliable the estimate of that mean value is. The standard error of the slope, so that's S sub b. That's how wobbly is this slope across samples. And so the more wobbly, the higher are the standard error, and therefore the larger this interval is. The last part of this formula is how far is the value we're trying to predict, in this case it's the value 5, from the mean. All right, so values around the mean, if you look at a scatter plot, the values around the mean are going to be the most stable because they've got a lot of data on both sides. Hopefully, it's somewhat intuitive that a value way off on an end, so here's a value that's far from the mean, or these values are far from the mean, those values are going to bounce around a lot more across samples because they're sitting off on the end of this regression line. So small changes in the slope produce big changes out here, much smaller changes out here. All right, so if we have sampling variation in the slope, you're going to see more effect out on the extremes than in the middle. The other type of interval is called a prediction interval. So the prediction interval is really talking about the distribution of y for this x. Now, let me go back and scribble a little bit. So if we draw the basic model, here we go. So here's our basic model again. You have a line, and where did this line, where did the scatter plot come from? Well, we have a normal distribution around that with standard deviation sigma sub e. Now, using the empirical formula, if we knew sigma sub e and we knew the regression line, then 68% of the cases would fall within 1 standard deviation, 1 sigma sub e, of the regression line. 95% will fall within 2 standard deviations of that regression line. Okay, so that's what we know. However, what happens if we don't know sigma sub e and the regression line for that matter, and have to estimate it with data? So if we're going to use data to estimate this regression line, there's going to be some sampling variation associated with both our slope and our intercept, as well as our estimate S sub e, which estimates that sigma. So prediction intervals account for this wobbliness due to the sampling variation. So this, let's just take a look at what happens if we have a giant n. So if you have a giant n of 1,000,000, say, well, 1 plus 1 over n is about 1, and we're just going to go, this is S sub e. And then what happens here? Well, if you had a sample of 1,000,000, usually your estimates of the slope become very reliable, and this term would go to 0. All right, so if you had a giant sample size, this whole formula then is just S sub e, and S sub e is going to be very reliable, and it equals sigma sub e. So then, you go 2 standard errors out, and it's just the empirical rule. However, to the extent that your estimates are not reliable, this is going to make the standard error a little bit bigger. So if your sample size is small, let's say it's only 10, then you take 1 plus a tenth, and S sub e gets magnified by then, you're multiplying by 1.1 instead of just essentially 1. To the extent that the regression line is wobbly, well, that's going to increase this as well. So to get these in R, you just change the formula from confidence to prediction. And here's the result. So this is going to give us a 95% prediction interval. The interpretation is this. Okay, I expect sales of 261 when I have 5 ads. However, there's a distribution around this. 95% of the time when I put 5 ads on the air, my sales are going to be between 137 and 287. So this 287 gives me, in essence, an upper bound for what I think my sales could be. It's very rare that I would ever observe sales more than 387. So if I wanted an upper bound for how much product I'd need, I could use that. You'll note that these numbers are going to be much larger than the confidence interval for the mean, and that's because this is just telling you how much is the mean going to bounce around. This is going to say how much is the entire distribution going to bounce around. So between 137, 386. And again, this is roughly 2 standard errors out from the mean. So the standard error was about 60-ish. You go 2 standard errors, let's go 120. So if we go 120 plus 261 is about 380. If you go 2 standard errors in the other direction, you're at about 140. So, that going 2 standard errors gets you in the ballpark. This is a little bit more precise. So those are all the basic tasks that we have to do with regression analysis.